By now, we already understand the normal stress and shear stress. So let's revisit a cow member centric axial loaded member. Cow member. So have a member and the load applied in the longitudinal axis of that member. And when we study the normal stress, we make a transverse cut. So basically, it perpendicular to the longitudinal axis. Now let's make a random cut AA, and form an angle theta from that transverse cut theta. And we want to see what will be the internal forces and what the stresses have on that cut AA. So let's consider the left segment of the cut. Left segment. So we have that cut here, and we have a load P, the same. And now when we cut, we have shear force on the cut parallel to the cut face, and then we also have the normal force N perpendicular to the cut face, and then we also have the bending moment, internal bending moment, MI. So if we call that area of that cut is the area of the cut face, and that A apostrophe, it will be the area of cut face. And AT is the area of the transverse cut. So if we suppose we can make a cut perpendicular to the longitudinal axis, that we call it AT, and that AT here is the area of transverse cut. So it will be area of transverse cut. So let me zoom in that areas. What is the relationship between the A apostrophe and AT? So with that, and you can see with the areas we have, that is the AT, and then the areas of that cut face, it will be A apostrophe, and the angle theta measure from the transverse cut to the cut AA, so that theta, it will be here. So with that relationship, A apostrophe basically the hypotenuse, and AT is adjacent to the theta, so we can see the relationship cosine theta equal to adjacent AT divided by A apostrophe. So from that we can have the A apostrophe, area of the cut face, AA, it will be equal to the areas of transverse cuts, so transverse areas, AT, divided by the cosine theta. And as you can see, the A apostrophe is 10 to greater than 80. So from that, what do I have? So if we take the equilibrium equation for the left segment in x direction, we can have N equal to P cosine theta if we apply sum of all the force in x direction. Why that? As you can see, that one equal to theta there. So sum of all the force in x direction, we have P cosine theta. Similarly, if we have sum of all the force in y direction, we will have the V equal to P sine theta. And of course, for the cowl member, we always have the internal bending moment, MI, is 0 for all cowl member. Because the load applied along the longitudinal axis of that member. For all cowl member, internal bending moment equals 0. But if we make a cut other than the transverse cut, we have normal force and shear force. And as we already know, the normal force creates the normal stress, shear force creates shear stress. So in this case, as you can see, we have both normal and shear stress. So let's talk about the normal and shear stress. And normal, we had that here sigma, and shear stress, we have it tau in here. So we have two components appear at the same time for this cut. So we already have the equation for the normal stress, sigma. In that case, it equal to the normal stress divided by the areas. In this case, the area A apostrophe for the cut form an angle theta from the transverse areas. And at n equal to P cosine theta, we can plug in cosine theta. And A apostrophe equal to AT over cosine theta that we already had there. So we have it AT over cosine theta. So with the transformation, we can have sigma, the normal stress for this, equal to P over AT and cosine square. And that we box for that equation. So for normal stress, for a cowl member, if we cut an angle theta from the transverse, then the sigma, the normal stress, equal to P over AT cosine square theta square. And similarly, we can have equation for the shear stress tau for this cut equals to, similar, it equal to shear force divide the area A apostrophe, and plug in for V equal to P sine theta. So P sine theta divided by A apostrophe, transverse areas, divided by cosine theta. So from that, we can have tau equal to P over AT sine theta cosine theta. So let's box that one. So that you can see, even a cowl member, if we make a cut from a theta from the transverse cut, then we have both normal stress and shear stress. So with that, let's apply to one problem that we already done. So let me revisit worksheet 1C, where we have a truss, right? So let's revisit to demonstrate this scenario. So let's talk about the worksheet. One C, and just revisit. We already done that. For those of you don't recall what is that, let's look at the solution and the video for worksheet 1C. So in revisit, if you recall, the member HI have 25 kips in compression. So let's make that cut for that member. 25 compression. So here that compression, so the force will be go into the cut 25 kips. And if we cut angle theta equal to 30 degree from the transverse cut theta, so let's want to find out the sigma and tau on this plane cut. So let's determine what is the question. We want to determine sigma normal stress and tau on plane cut in member HI, in that we do it in worksheet 1C, member HI at theta equal to 30 degree from transverse cut, from transverse. So from that we can apply the two equations above immediately. So we have sigma, the normal stress on that member, equal to P over AT cosine theta square, plug in it, P equal to 25 kips, and in this case in compression, and over AT, and AT in that case, if you recall, it will be 4 inch square, and then cosine 30 degree square. From that we can have sigma equal to 4.69, and the unit is KSI, kip per square inch, 4 inch square. And with that, it in compression, so that one also in compression. That is for sigma. And for tau, we do the same with the equation. So tau equal to P over AT sine theta cosine theta. P equal to 25 kips, AT equal to 4 inch square, sine 30 degree, cosine 30 degree. And from that we can have tau equal to 2.71 KSI, and that's the answer for the tau. So as you can see, for the member HI is a tau member with 25 kips in compression, but if we cut the angle theta from the transverse 30 degree, we have both normal stress and shear stress. In this case, normal stress 4.69 KSI, compression, and tau equal to 2.71 KSI on that cut, here. So that is the normal stress and shear stress. So the next we're talking about the states of the stress. It will be a very tricky concept, but let's get through that, and also remember that because we will revisit state of stress when we do the stress and strain transformation in later of this semester.